So with that, I would like to start our next session, which is the lightning talks from our EAI faculty. And I'm happy to showcase our faculty. As I've said earlier this morning, we comprise a multiple group of diverse team of faculty from all areas, from computer science, engineering, science, and math, to social science, psychology, to ethics, to law, and to arts, media, and design. So we have faculty across all areas trying to solve grand challenges in society, and it's unfortunate I can't have all of them talk because they do wonderful research, but I picked some representative 5 examples of faculty coming from diverse areas impacting health, climate, and cybersecurity, and also supply chain and humanitarian logistics. And also they come from also from diverse stages in their career as well. So our first speaker is Özlem Ergun. She's our distinguished professor of mechanical and industrial engineering, and she focuses her area in design and management of large-scale and decentralized networks, and she does a lot of work in supply chain and humanitarian logistics, and has worked closely with organizations that respond to emergencies and humanitarian crises around the world, including USAID, CARE USA, FEMA, CDC, all of them. And she was also the president of Informs on public programs, service and needs in 2013. She is a co-chair, a founding co-chair of the annual Health and Humanitarian Logistics Conference that's held annually since 2009. So I give you Özlem.
All right, thank you, Jennifer. And I should put this up, make sure. I have 10 minutes. So my background is in operations research, and really in my core, I'm a network optimizer. And AI to me means basically data analytics, and mathematical modeling and algorithmic development and algorithms to solve hard and complex optimization models. So I have spent 20 plus years, and one of the biggest application areas that I work in is in logistics and supply chains. And about the last 15 years, I mean, I've always worked with commercial supply chains and kind of the theory of supply chains, but over the last 15 years, I have done a lot of work using AI in humanitarian supply chains. And given that Jennifer wants us to kind of talk about all the wonderful things that AI can do in a diversity of fields, so I choose to talk a little bit about the work that I do with humanitarian organizations. And it works. Okay, so supply chains are kind of networks that enable stuff, materials to go from, raw materials to suppliers to distributors and other things to kind of the customers. In humanitarian supply chains, what we see is you kind of have the same enabling of distribution of products, but the supply chains are a little bit different in the sense that everything starts with money and the donors, okay? And it's very different. Like in commercial supply chains, you usually see that, there's a demand forecast and you start producing, and there is kind of the money to do that. In humanitarian and emergency supply chains, usually an event happens and demand already exists. And then the organizations go and try to get money to do their operations. And then the money comes in, and then the mobilization starts happening. So in that sense, humanitarian supply chains and emergency response supply chains have to be very agile, because they have to kind of work quickly and organize quickly. And they have to be, all supply chains, as we see on the news, in the top of the news every day these days, all supply chains have to be resilient. But the humanitarian supply chains have to be even more resilient, because they deal with much more unexpected type of demand than regular supply chains. Okay, but kind of the goal is the same. You want to, deliver the right product to the right people at the right cost. One of the most important things in humanitarian supply chains is that, the cost is important because with the same amount of money, you want to serve more people, but at the same time, delivery speed and the number of people you serve sometimes takes over the cost. Okay, and there is always, as in any supply chain, there is the tension between being resilient versus being efficient for ongoing demand. And that's a big, big, big tension because, we kind of want to make sure that we're not, running a completely inefficient supply chain with holding a lot of inventories and doing other wonderful things that would be very resilient, but then we would go broke. Even the humanitarian agencies will go broke. So I just want to briefly talk about, and I'll probably just talk about the first one. I have been working with the United Nations World Food Program for over 15 years, and it is the largest humanitarian organization in the world. And the reason that I've always been very interested in working with UNWFP is because their logistics and supply chains is the driving factor of their operations. Okay, so it's a global organization, it operates in more than 80 countries in the world. And the important thing, and one of their logistics chiefs, as one of their logistics chief used to say in the past, is that there is enough food to, kind of feed everyone in the world. The key is how do you actually get it to the right people and the needy. So their logistics operation actually is one of the biggest cost centers in their operations. Okay, so whatever you do in logistics and supply chains actually impacts their bottom line in a huge way. So when I started working with WFP Supply Chains exactly 10 years ago, they actually had an organization where everyone, or all the functions worked in silos, right? So there was a group who decided on what should be the food basket for a given program. And then there was another group which decided what is the modality of the delivery. Do you give cash and vouchers to the needy, or do you actually bring the commodities to a location, right? And then once they decided, it went to the procurement group, and who decided where to procure things around the globe. And then they told them this is what we're procuring. They told the logistics organization, this is what we're procuring, bring them here. As all of us kind of think about networks, systems, you can see that this is a very inefficient way of doing things because, sometimes just doing a small replacement in the food basket may actually save a lot of money in procurement and logistics. So if you're not doing these things jointly, you're actually losing a lot. But what do you need? To do all of these things together, right? You first need the data. You have the data transparency. You need all these people to talk together, and you need to have the framework and the tools that enable them to make joint decisions. So that's the optimal goal. So we work with them for over a decade. We first did a huge data project. When I first started working with them, it was kind of the data exists. The guy who bought that one truckload of transportation in Ethiopia knows that cost, but nobody else in the headquarters or in the organization knew the cost of transportation. So we did a huge data project, identifying what is the crucial data, how to actually organize it, store it, and make sure that it can be shareable across their global organization. We built mathematical models based on networks. I'm a network person. I do everything in networks. And then we actually created tools that are kind of nimble in the sense that it is both helps decision-making in the headquarters with all the data and the resources and the infrastructure, but it's also kind of parts of it can be used in regional and country offices in kind of more limited infrastructure settings. So this has been a really, really successful project. My biggest, proudest moment is when actually in their annual report, their supply chain group said that the solution uses mathematical algorithms to assess all available options and propose optimized supply chain setups. Having that mathematical algorithms in a humanitarian organization's annual report is a success, because I mean, I think someone in the previous panel talked about like, how do you even like get people to accept these kind of solutions? And humanitarian organizations is one of the least technical groups that you can actually, you know, see or interact with. So this was this and other things, like we helped them actually to build an analytics group within WFP. It's been growing, very successful. You know, I'm not taking the credit for them getting the Nobel Peace Prize, but the year after, last year, we actually won the biggest applied operations research prize we can get together with them from the Informs organization. But more than that, every year they can show like millions of dollars saved. Furthermore, not only millions of dollars saved, but actually, you know, like showing real reductions on lead time, or, you know, like reaching the beneficiaries quicker. And it is, you know, like it's kind of like recorded factual every year. It's repeated. So I mean, given my time, I'll stop here. But just to show you, we actually very recently finished a similar type of project with USAID and their Food for Peace program. In this work, we also work with their supply chain group and developed a supply chain optimization tool. I would say the one thing that was kind of different is that we did here was really we some of the problems that we looked at very seriously considered looking at ongoing demand, but at the same time like emergency demand or sudden onset demand. So we built on top of what we have done in the WFP, we built kind of stochastic optimization models that kind of looked at scenarios and did risk analysis, which was also a big challenge. You know, kind of like even understanding what is the risk and the risk profile was an important part of this work. But I'll finish here. Thank you.
Thank you so much, Aslam. We'll have questions at the end, so just hold on. Our next speaker is Arup Ganguly, and he's going to be joining us virtually. So is he on? He is a professor of civil and environmental engineering at Northeastern, and he has several affiliate appointments with Corey College of Computer Science and also the School of Public Policy and Urban Affairs. His research intersects weather and hydrologic extremes under climate change, and he also looks at infrastructure resilience under these extreme conditions. And interesting thing about Arup, he also works and does research in machine learning and nonlinear physics. He has a joint role as chief scientist at the Pacific Northwest National Lab, and he also co-founded the Boston-based climate analytics startup RiskQ. So you can see the impact that he has been doing, both in academia and also in industry. Plus, he has also been in review panels in United Nations Environmental Program and other US and global agencies. With that, I will give you Arup. Are you there?
Wonderful. Thank you so much. So today, what I'll present is what I presented just a couple of months back in National Academy's workshop, which was titled Machine Learning and Artificial Intelligence to Advance Earth System Science. And the specific panel where I was asked to speak was about emerging opportunities from social and human engineered systems. I thought this talk would be particularly relevant, and it is fairly recent. Aslam's talk provides an interesting segue to what I'm going to discuss a little bit. She talked about the United Nations panels. Some of you here may be aware of the Intergovernmental Panel on Climate Change, which is the UN body that won the Nobel Prize also for peace, though, in earlier 2007. And so the last three reports from the IPCC, as they are called, comprise AR6. This is Assessment Report 6, or the sixth assessment report. This is a regular assessment report that the IPCC publishes, and they publish in three areas. The first one is physical science basis. The second one is impacts, adaptation, and vulnerability. And the third one is mitigation. I think, talking about interdisciplinarity at Northeastern, I think we are probably one of few academic labs from where each of these IPCC reports actually cited some of our published work. Okay, with that, let me just set the stage here. So here, what I was asked to talk about is machine learning and artificial intelligence in the context of climate resilience, including how these emerging opportunities relate to social and human engineered systems. So our ability to surmount the barrier of what may be viewed as convergence of complexities at the intersection of coupled natural, human engineered, and social systems is perhaps among the most difficult yet consequential of the challenges we face in climate resilience. So here I'll examine the possibility that AI, in combination with science, engineering, and social science theory, along with policy frameworks, can rise to that challenge. Next slide, please. Trends and natural variability in Earth and natural systems impact and are in turn impacted by human engineered systems such as large-scale interlinked infrastructure and lifeline systems in water, energy, communications, and transportation. Natural and human engineered systems are further interlinked with social or human systems such as urban or rural communities, financial services, human institutions, regulatory frameworks, and governance mechanisms. Physics-guided, uncertainty-aware, spatiotemporal machine learning, including computer vision, have shown early promise in natural Earth systems and in translating predictive understanding to stakeholder-relevant products. Probabilistic graphical models and graph mining methods, such as complex network science, social network analysis, and Bayesian networks, have demonstrated promise in the resilience of interlinked infrastructures and social systems. Agent-based models, gaming exercises, and game theoretic constructs, as well as participatory modeling with human AI interfaces, have shown promise in the human and social sciences. I feel what is still lacking, however, is progress toward developing or implementing holistic risk and resilience frameworks that consider the flow of uncertainty and causality both in forward and in feedback modes. Next slide, please. So while that slide was somewhat aspirational and something I think none of us can do alone, certainly I cannot do alone, here I will provide some illustrative examples from our own work. On the left, it shows a paper which is in review, available in preprint archive, which develops explainable deep learning methods for predictive understanding of El Nino and river flows around the world based on sea surface temperatures, or SSTs. Showcasing our interdisciplinary work at Northeastern, this is joint work with Professor Jennifer D, from whom you have heard here, and both of our now former PhD students. So the primary hypothesis there is that variables such as SSTs, sea surface temperatures, which are predicted relatively better by Earth system or climate models, have information content about stakeholder relevant processes and variables such as El Nino and regional land hydrology, which may not be so well predicted. And this relationship can be learned from observations first, and then superposed on models for better predictive understanding. The middle panel shows a paper published in one of the highly selective AI and data science conferences, specifically ACM's Knowledge Discovery and Data Mining, or KDD, which I believe Dr. Usama Fayyad was instrumental in co-founding, or had a big role. So this approach developed a novel method for uncertainty quantification in the context of deep learning for translating Earth system model simulations to stakeholder relevant predictions. And on the right, I show a paper, one of our papers in Scientific Reports, which developed resilience insights for the London urban rail transit system subject to floods and compound extremes, specifically floods of the future and opportunistic attacks, based on network science and graphical methods. Next slide, please. So you heard a bit about this company Risk. So this climate analytics startup company Risk, which you can learn about from www.risq.io, was co-founded by me and two former Northeastern alums. One of them, Evan Kodra, who was the CEO, was my former PhD student. This goes beyond research products and attempts to develop real-world solutions in the context of climate and cities. In fact, to the best of our knowledge, this is probably the first case of a successful quote-unquote exit of a startup directly in the intersection of cities and climate, even though successful climate startups do exist in other areas such as agriculture and reinsurance. In this case, one important lesson learned from this journey of risk is that in these markets, data science products and financial incentives or social imperatives must be developed in tandem. The startup, which has been recently acquired by a Fortune 500 company, develops 3 product suites: physics-guided data sciences for grounding climate model simulations and observations to the needs of urban stakeholders, climate risk to investment benchmarking through economics-informed data sciences, as well as data-driven climate justice products that examine social impacts on underserved populations based on geospatial data sciences. With that, I will stop here and yield the floor, please.
Thank you, Arup. Okay, so we're gonna move on. So Arup, the questions will be at the end. So hopefully you can stay on for later. So, thank you. The next speaker is Byron Wallace, and he's an associate professor at the Curry College of Computer Science. And his research area is machine learning, AI, and natural language processing, and also applications in health informatics.
Oh, cool. All right. It works. Hi, everyone. Thanks for the introduction. Thanks for having me. This is a super fun session to be a part of. So, right, I do mostly natural language processing with applications to healthcare. And I thought what I would do today in this kind of brief talk is, I guess, just give a sense of a few of the specific challenges that we've been trying to work on, and I guess like the sort of technical problems that these give rise to. So this will kind of give, I hope, a flavor of the kind of things that we're sort of trying to do. Let's see if, oh, does it want to do it? Maybe. It's not happening. Does anyone know anything about computers? All right, here we go. Okay, so, right. So the problem here, I guess, at a high level is that a lot of the data in healthcare, I guess, generally speaking, is unstructured, right? So there's all this evidence out there. In one form, this would be kind of, for example, the biomedical literature, unstructured text. Another form, as an example, is electronic health records, right? So there's a lot of clinical notes that are, of course, in natural language. So we'd like to use NLP technologies to kind of help physicians and other healthcare providers make sense of and ultimately use this data to improve patient care. So that's the dream, and I'll talk very briefly about like sort of 2 specific cases. So one case is this idea of trying to synthesize or summarize the evidence that's reported in articles describing clinical trials, the conduct and the results of those. And then I'll just kind of allude to some other work that we've been doing on trying to help radiologists make use of information that's buried within the free text fields within electronic medical records. So, right, so for a couple of, so the problem here is that we have this system where somebody goes off and they do a clinical trial, And the way that they disseminate the results of that clinical trial is via an unstructured journal article that describes the results, right? So this is not a great system. And what it means in practice is that it's very difficult to go out and try to assemble, what is the best evidence for the use of a particular intervention for some specific, condition that you might have. Right? So for a number of years, we've been trying to build natural language technologies that can, sort of effectively read, let's say, clinical trials literature, and ultimately try to sort of extract from this the information that's of interest, namely what are the interventions that were studied, what were the comparators, what were the outcomes that were measured, and ultimately what was found to have worked or not. So that's the kind of idea. And so I guess we've put this together into, we sort of have all these models that we've built up over the years. And this is a collaboration with a real doctor, Ian Marshall, who's shown here. He's in London. And so what we've done is we've sort of taken this suite of machine learning models that I won't talk about, and we've put them all together into this system. And what we do is we apply those models to new evidence as it is published. And we aggregate that into what we call this trial streamer database, which is a continuously updated repository of this semi-structured information for all published trials that we compile in real time. And I want to give a huge shout out to Osama and the Institute for, they've become our new home for trial streamer. So you see this URL here. And they've been integral in letting us sort of get this up and running. And so, yeah, so we sort of extract all these fields. I'm not going to get into the details. I'll just show you the picture. So like here's sort of the prototype interface. We also make all the data that we extract like available. And this gets updated every day. So I guess when I took the screenshot, it had been updated 20 hours ago. And we index about 780-ish thousand clinical trial reports. And what you can do is you can kind of like run a search. So you run a search for example, COVID-19 and ivermectin. Ivermectin being some intervention that you might be interested in the outcome. And there's this very recent trial that came out that we found. And what we see is we surface, for example, the number of patients that were randomized, which again is actually not readily available, right? Like there's no index of that on like PubMed. You have to extract that using NLP. And then also like we try to extract what seem to be the main kind of takeaways of the trial. We call these the punchlines. And we extract other things as well, like descriptions of the populations, the interventions, the outcomes. And we try to assess like the risk of statistical bias, which is sort of a function of like how well the trial was executed and designed. And we do all of this with NLP. Right, so that's the idea. And I guess one of the challenges that's sort of technical challenges that this surfaces, if you're trying to present this kind of information to let's say a primary care physician, you really need to be able to provide, you don't want to just be like, okay, the model has sort of read this trial and thinks that ivermectin is not effective. You need to be able to tell them why the model says this. So we've done a lot of work as a function of this, trying to rationalize neural predictions, by which I mean basically provide a snippet of text that's extracted from the underlying article that supports the inference that was made pertaining to the efficacy or lack thereof of a particular intervention like ivermectin. So this has given rise to, we've done this in the kind of clinical trial space, but we spun this out. So this was the motivation, but then we also, so we use this to kind of design new kinds of models that basically do this rationale extraction for neural NLP models in a specific way. And the idea here is like you sort of first conditionally identify a snippet that's of interest to a particular query, and in like this sort of pipelined way, you pass that forward to a predictor model, and it makes a prediction just on the basis of that snippet. And this provides or permits a very natural kind of interpretability. And we sort of spun that out into looking at that task more generally, right? So not just in the clinical trials space, but looking at this from a more general kind of NLP space. And students of mine here shown are Jay and Sartak, and they kind of led this work where we put together this benchmark that we call Eraser for doing rationalized neural prediction in NLP, right? So this was an example where we started with an application and then kind of spun that out into, I guess, a sort of mainstream CS research contribution. And this has been picked up reasonably widely by the NLP world. Right, so what we'd like to move towards is we want to actually go further. We want to do actual narrative synthesis of the evidence. So basically you want to be able to put in, like, look, I'm interested in what the evidence has to say in aggregate about COVID-19 and ivermectin. And so what we'd like to do is basically output an actual narrative summary that synthesizes all of the evidence. And this is an actual example. We have a little prototype implementation of this that I have locally. It's not available publicly for reasons you'll see in 1 second. And it does generate things that look pretty plausible. Like this one's actually pretty good. So we're at a place now in NLP where you can generate like really good text, right? So we're very good at conditional generation now, which even a couple of years ago we couldn't really do. And so we're using, I'm not going to get into it, but we're using like a standard multi-document neural summarization approach, at least as a start to do this. And in particular, we like to name things after like cartoon characters in NLP for some reason, and like Muppets. So anyways, this particular one is called BART. And what happens is, and the reason that we don't make it public yet, and it's still a research problem, is like even though the text looks really plausible, here's an actual example from like if you search for like SARS-CoV-2 and some vaccines, it says, okay, look, vaccines cannot be recommended for routine clinical practice at this time. And like the rest of it is like pretty plausible. It's like, oh, you need more RCTs. And like that makes sense because like that's actually a pretty likely snippet. Most things aren't very well supported by the evidence. But this one actually is, right? So I don't know. So yeah, it's a problem. So we're working, this is like another kind of challenge that's spun out of this, right? Which is that we have all these factual errors and they're not controllable. So we're working on this. So Sanjana is shown here. She's one of my PhD students that's kind of working on more, I'm not going to get into the details, but working on more sort of explainable or controllable and hopefully less prone to error systems for doing this. The last thing I'll just mention very briefly is we've been working with Jeff, who's the doctor shown there. He's a radiologist at Brigham and Women's. This is work led by Jared, who's shown there. He's another PhD student. And we're trying to kind of summarize electronic medical records for radiologists at point of care. And the problem here is that we don't have enough supervision, right? So these models are very data hungry. So you have to kind of try to come up with ways of supervising these models that isn't going to take all of Jeff's time because he doesn't have any time. So that's sort of the last one I'll talk about. And yeah, so we're sort of working on it. I don't want to go over, so that's my TLDR. And thanks again for having me. And I'll stop here.
Thank you, Byron. So our next speaker will also be in health, Sarah Ostadabas. She is an assistant professor at the Department of Electrical and Computer Engineering at Northeastern. And her area of research is in enhancing human information processing through the design of adaptive interfaces via physical, physiological, and cognitive state estimation. My shortcut for that is that she's doing signal processing, computer vision, and post-estimation. And then also she works on applications with augmented reality and virtual reality tools to help as well. And she's applying this to health. And also I'm proud to say that she recently won the NSF Career Award as well. So.
Thanks, everyone, and good afternoon. First of all, let's thank Osama and Jennifer for arranging such a great event and for inviting me. I'm Sarah Ostadabas, an assistant professor of electrical and computer engineering at Northeastern University. My research interests are at the intersection of computer vision and machine learning, with particular focus on representation learning in visual perception problem. On the applied side of my research, my algorithm primarily contribute to understanding, predicting, and detecting human or animal behaviors by estimating their physical, physiological, or emotional states. For a robust and efficient state estimation, my algorithm tries to represent the state of the world in a low-dimensional embedding called pose, as Jennifer mentioned. So I do a lot of pose estimation. And the pose is this low-dimensional, interpretable, and succinct representation of the important information in the state. I do a lot of pose estimation. Here, for example, you see we do Parkinson patient body pose estimation to understand Parkinson behavior after a specific drug delivery with Pfizer. Also, we do even bat flying pose estimation to help roboticists to design flying drones. One thing that is very common among all of these pose estimation is the need for data, a lot of data, and we are hearing about data here. However, something that makes it interesting and novel the lab that we are doing, that we are working on the area that data collection or labeling is expensive or even impossible, or is strongly protected by strong privacy or security laws. You could imagine a lot of healthcare application and application in the also army and defense. So for those, we still need to have this model. We need to bring the AI into the picture. So what we do here, I try to make sure to combine two lines of AI here by first making the domain knowledge inside the generative model to augment the data by synthesizing enough data that is needed. And then on the other side of the coin, I'm also trying to make use of the advanced data-efficient machine learning that have been used, like unsupervised learning, like zero-shot learning. So all of the very powerful data-efficient machine learning tools. Let me start as an example. I don't think I can go to all of those examples that I show, but I want to focus on one interesting small data example, understanding infant pose. And why is it important? Because it has been shown that in the last few decades that understanding motor behaviors and motor function of infants can lead us to prevent a host of developmental disorder, including autism spectrum disorder, cerebral palsy, and among a few other disorders. So it's very important to understand that, and baby monitors are everywhere. But if you have a baby monitor that you are using that for 24 hours, it means that you need 24 hours to sit and watch that. So what we do, we want to do pose estimation automatically on that and start extracting specific behavioral and motor function from those. Thanks to deep learning, human pose estimation has received a lot of attention and success lately. However, unfortunately, a lot of these success cannot be translated when it comes to the infant pose estimation. If you look at the adult poses, which all of these models have been trained on, you can imagine that there are big data of the adult poses from social media, from Hollywood images, from sport, and they are labeled available. They're not going to work with the infant poses. Infants, they have much more complex and unique type of poses that they can get. One other thing, infant body shape is already different. Infants are human, but the body shape is different. The muscle to bone ratio is different. So models, 3D model trained on the adults doesn't work on infants. So I wanted to show you actually this huge data gap. We were talking about the data gap that the model that trained on one doesn't work. Let me actually show you examples from the feature domain. So using the data that's coming from the COCO, Microsoft COCO dataset, the adult dataset coming from different sources, and then comparing it for infant dataset, we actually clearly show that there is a distinct distribution gap between those data, which means that if I have the model trained on the blue color, it's not going to work on your purple, whatever color that you call it here. So what can we do here? Remember I mentioned I try to combine these two strengths of the AI. First, generating and expanding the data set by augmenting the data that we have in hand. And the second, bring the advancement of the data-efficient machine learning into the picture. Quickly go through that. We do data augmentation. We are using some of the template-based model and fit that to the infant data. We also go beyond that. We actually look at some of the game engine. We look at the avatar and start reposing those infants. The good thing about those is it allows us also to bring diversity. Although the infant pictures out there, they are not a lot, it's very hard to actually find, because of the privacy issue, infant pictures out there. But you can make the infant avatar from with different sizes, different races, and put them in different background. So we can actually expand the data distribution here. So look at that. Also, I can put infants in dangerous or specific types of behavior if it's avatar. So here we use specific types of avatar, but then you can actually make it on different background, and we have done that. Having said that, it's not enough. All of these data, you saw that adult and infants have different, very distinct data distribution, but synthetic data and real data also have the same thing. So we have to make use of this adjacent domain data set, but also make our model robust in the specific domain. So my group has been developing this domain adapted and fine-tuned approach that allows to close this gap between these distribution. I'm not going to go to the details of model. However, let me quickly to show you what's going to happen. First of all, remember that synthetic data set that I'm generating also by addition of some of the data set that our lab is the first lab group that publicly releasing this data set, allows to increase the accuracy of pose estimation when it comes to infant pose estimation. Also, we apply our domain adaptation tools, and we see that here, when we have original distinction between two domains, we can get the domain confusion. We need domain confusion here. We want the model to not recognize where the data sources is, so to be able to learn from different sources. And then here it shows that the state-of-the-art computer vision that works, OpenPose, everybody knows that, on several humans, on doing all of those complex things. It doesn't work on infants when they are cruising or climbing the stair, but our model robustly is able to follow infants, and hopefully can be, this system can come to the picture and be in every baby monitor out there. Thank you so much, and I just want to thank my lab and all of my collaborators, and also the funding agency and industries. Thank you.
Thank you, Sarah. And also I would like to make a plug for Sarah will be presenting again with a longer platform at our Experiential AI seminar next week on Wednesday at 1 p.m. Okay. So our last speaker today is Alina Oprea. She's an associate professor in the Curry College of Computer Science, and I'll just make it short. Her area of research is machine learning and cybersecurity.
Okay, thank you so much, everyone, and thank you for inviting me to give a talk at the opening of the Institute. I really appreciate being here, and I'm going to talk about something completely different than everybody else, and that is the use of AI in cybersecurity. Let's see if this works. Oh, great. Okay. So I don't want to scare anybody here, but we read a lot about security breaches in the news. We see a lot of cyber attacks all the time. And the famous cyber attack was the RSA attack back in 2011. And this started the new era in sophistication of cyber attacks. And since then, we have seen more and more attacks, more diverse behavior. So just to give some examples, the WannaCry ransomware attack in 2017 was able to propagate independently on the internet to more than 200,000 machines in just a few days. And last year, we have seen the Colonial Pipeline breach, which caused the shutdown of an entire oil pipeline in the Northeast for 6 days. So there is huge impact of these cyber attacks, a lot of financial losses, loss of sensitive information, private information, as well as critical infrastructure threats. So the question that motivates my research is if we can use AI to solve these security problems to actually improve the existing cyber defenses. And some of the things that we would like to do with AI is be able to detect attacks much faster and better than existing defenses, because the existing defenses simply don't work, have fewer errors, and eventually deploy mitigations against these attacks to prevent cybersecurity breaches completely. But this is not an easy problem, and it's not as easy as taking the AI tools and just apply them to cybersecurity, because there are a number of challenges that have been recognized in the domain, and I like to mention some of them here. So first of all, the security data set, the cyber data, cannot be publicly shared on the internet in order to train machine learning models, in contrast with other domains like computer vision or NLP, where there are public benchmarks that are available. In cybersecurity, all this data is private and includes a lot of sensitive information. And then there are certain temporal and spatial semantics in the cyber data that make the models deployed for other domains inapplicable in cybersecurity. The cost of error is pretty high. If we err on either side, with false positives, we are generating more work for human analysts to investigate the detections. With false negatives, we are simply not detecting attacks and we are breached, so the cost is pretty high. And finally, one of the unique aspects of using AI as a cyber defense is the fact that the AI might be under the attack from against advanced adversaries. So they really have to be resilient against attacks. We're talking about nation-state or very well-funded adversaries here. So I like to briefly talk about two systems that we built in my group that try to use AI for cyber defense. And I'm not going to have time to go into a lot of details, but both of these systems are funded by the DARPA Chase program. The first one is a system for attack detection at the level of a single enterprise or a single organization. This we call PORTFILER. And the focus of this is to detect self-propagating malware attacks such as WannaCry or Mirai. And the way this system works is by monitoring the logs, the network traffic inside an organization. We build a training time, a profile of the normal traffic, normal behavior that evolves over time. And then a deployment time, we try to detect anomalies and events that deviate from that behavior and also rank them and present them to an analyst for investigation. And so the key innovation here is that we design an ensemble model that is resilient against evasion. And we perform evaluation on very large data sets using two university networks with more than 1 billion logs daily and several malware families. I have some results here, but I'm not going to go into a lot of detail. The bottom line is that our proposed ensemble method is more resilient than existing models such as kernel density estimate. I'm showing here a precision recall curve. And here I'm showing some performance number regarding precision and false positive rates of our system. But the most important thing I want to mention is that this system has been deployed in 2 university networks, and it was able to identify a set of 76 new malicious domains, new malware that was not detected by existing tools, and it was confirmed as malicious by security teams that manually verified this incident, right? So we can not only discover the attacks that we already know, but we can use AI to help discover new attacks that we don't know about. And a second system that we built is now looking at a global defense, trying to use AI to build a global level cyber defenses. This is a system that we call PCOR, and this is relatively recent work, right? So in the first system that I talked about, and most AI-based systems for cyber defense look at a single organization, a single network, try to detect attacks inside the single network. But the idea here is to design a collaborative cyber defense system where everybody can collaborate and together train a global model that will protect everybody against cyber attacks. And here we are using techniques from federated learning for this idea of decentralized learning. We call this PCOR, Privacy Enhanced Coordinated Enterprise Defense. This is focusing on detecting malware command and control communication, which is a standard phase in many cyber attacks, and it works on HTTP data, which is very common type of data in cybersecurity. The main advantage of this system is that it's privacy preserving, right? So in order to participate or to contribute data to this system, you don't have to share the raw data, but instead you can share model parameters, and so the system is trained globally while preserving the privacy of the security logs. And I have here some results, but the bottom line here is that the federated model performs better than a local model that is trained at a single organization. I'm not going to go into the details of the numbers because we're running out of time. So I talked briefly about 2 successful systems for detecting cyber attacks. One is at the local level, looking at a single organization or single enterprise, and the second one is a global level cyber defense. The main challenge, I would say, in this space on using AI for cybersecurity is to make the model resilient against cyber attacks. And this area of adversarial machine learning started to gain a lot of attention since 2013 with the work of Sedeghi and others, which discovered the adversarial examples. The fact that deep neural networks are in fact not resilient against very small manipulation of their inputs. And so those are called evasion attacks, and we have done a lot of work on evasion attacks for cybersecurity as well. In addition to that, there is another threat in adversarial machine learning that is often overlooked, that threat of poisoning attacks, when an attacker has access to a subset of the training data. And so we have shown that this is also a real threat in cybersecurity, in particular in malware classifiers. And so I guess to end, the takeaways of my talk are that AI has a lot of potential in cybersecurity. We can use it to improve existing defenses and to build this global level cyber defenses. But at the same time, AI itself could become the target of attack. And we have to look at both evasion and poisoning attacks. There are a range of attacks from adversarial machine learning that are particularly relevant in cybersecurity. And so more research is needed in designing resilient AI algorithms. And with that, I would like to thank you, and I'm happy to take questions at the end. Okay, thank you.
So are there questions? And in the meantime, I'd like the speakers to sit here so that they can answer the questions. We have a few minutes. We have 5 minutes to answer questions. And maybe, okay, Arup is there now. Okay, just sit on the chair with a mic, anywhere. So are there questions to any one of the speakers?
I'll bet NLP can help all the way from the stuff Arup is doing to the stuff you're doing, Alina, to, you know, Özlem also, and you, Sarah. Is that too far a reach? And why aren't we kind of leveraging that? I'm just curious. It's not a criticism. I'm just curious.
As the NLP person, of course that's correct. You know, yeah, obviously. You know, I would be interested in getting there, but my impression would be yes.
Yeah, definitely. I mean, I would say in cybersecurity, in fact, we are using NLP for this application for HTTP logs. We have a semantic-aware embedding-based representation. It's just not unstructured data, like Byron was saying in the healthcare domain. Our data is much more structured. There is a temporal dimension as well, which needs to be captured. But definitely, I think there is a lot of opportunity for NLP.
I mean, I think my answer is kind of similar to yours. I don't know. Maybe this is on. I think like in the domains I work in, usually there's a big structure that you can actually take advantage of. So why not take advantage of that? On the other hand, I think like right now I'm doing another project for WFP, and it's a forecasting prediction project for malnutrition in Dakar area. There is no structured data. It's terrible actually, and we're trying to like get data from all these unstructured texts and reports, and yeah, so of course for that you would really want to have an NLP expert.
One of the things I would say as well about this is like from the modeling perspective, something that's simultaneously interesting but also making things a little bit boring in some ways is like this convergence to transformers for everything. And I think that the question was like, why not exploit the structure that's there? And I agree, like that like feels like what you want to do, but then in practice this depressing thing happens where the answer becomes because empirically you can just throw like transformers at it and it like does better, and it's really frustrating. But so like increasingly though, we are seeing this like convergence of architectures to like everything is a token and just shove it through a giant neural network, and like it does really depressingly well. And like, I don't love that that's true, but it, you know, I'm an empiricist, and so I think it's interesting.
But I think you're absolutely right. I mean, so in my field, more and more we see kind of learning-based, you know, models for inventory management and this and that, and then they do depressingly well. I agree. It's just terrible, and I'm building them now.
Yeah, Arup is saying something, and I'm curious what he's saying because his models are more physics-based. So
yeah, if I can add something. So first of all, quick comment about NLP. Yes, NLP is not just useful. We are using it, Jennifer and I, and a few other faculty from across colleges. We have a climate AI sub-program of the overall AI postdoctoral program, and one of our postdoctoral research associates, Antonia Swans, is actually using NLP for what I'd call mining policy documents about droughts, for example. So that's one question. The other question is, transformers can solve everything? Hell no. I'm sorry, but if that were the case, I work in things where physics and biogeochemistry and in some cases, engineering principles, social science theories have to be brought together. With machine learning, we have a traditional knowledge base, which we just cannot discard. In some cases, we have enough data. In some cases, we do not have data. We have a big data, small data challenge. The amount of data is vast, but when we try to go into the past, when we try to look at extremes, we don't have enough data. So no, absolutely not. There is no one architecture, no one representation, no one machine learning approach that can address all of the issues. And we have to bring together, this was a lesson learned as in our NSF size funded expeditions in computing. We have to bring together the theory that we have and the most appropriate data science tool that we have, whether it's linear regression, whether it's transformers, and no one representation will solve all of that. In fact, if you can, I'd welcome you. That would be great.
Okay, there's another question in the audience.
Yeah, it's a complicated question. I don't know if it's a question, but your example about the NLP model saying might not be ready yet. I was curious about, we talked earlier about biases and when is a human better at something, when is a machine better at something. And curious to know, how does supervision come into play when, as humans, we choose data that fits our narrative most of the time, and we ignore the stuff that generally doesn't fit our story, especially if it's a small enough data set. But computers can actually wake us up to things. And in your example, and I'm not making a political statement here, but your example is like, oh, maybe this isn't working yet because it says, vaccines might not be valid, but maybe political bias or human bias might suggest that they're not, that statement wasn't valid, but maybe it's an important piece of information. So where do we depend on things that we don't like or might not like to hear versus, things that machines are actually might be better at us for, especially around NLP and looking at that type of data. So how did you rationalize that, or how would you rationalize that going forward? Is there a bias coming into the point of judging if my model is accurate or not?
Right. So, okay. So I guess in that particular case, this is a somewhat limited domain where we know the sort of ground truth because you can actually do a statistical meta-analysis of the clinical trials or whatever. Or in this particular case, the clinical trials are very large, and it's kind of a unique case because the evidence is so solid. And so you just kind of objectively, if a human reads the actual trial, the system is just wrong. So I guess in that particular case, of course, more generally, yeah. So more generally, these huge systems that people train, pre-train in the jargon, they're fit over arbitrarily sampled internet text, which is, as you might imagine, not great. And so this brings, of course, all sorts of biases and problems, and there's a whole kind of subfield that looks at these things, and they're as racist and sexist as you would anticipate them being after being trained on the internet. So I think that, there's an ongoing kind of research thing. I wouldn't worry so much about like, oh, is this like actually telling us something we like don't? I see what you're saying. You're giving the models too much credit in some ways, Like, they basically, they'll reflect the distribution of whatever you feed them. And so I don't think that they're going to provide any like great insight in this sense. But this is obviously a real problem. And just one clarifying thing, I definitely don't think transformers are the solution or the one right architecture. I'm only remarking on their depressing dominance, and I hope you're right, and I want to believe you. So just for the record, I'm not like the Transformers guy, I mean, I use them, but out of necessity. That's all.
Anyway, let's thank all the speakers, and thank you for the audience as well.